I'm Alex Brown, and I'd like to introduce you to the Bare Deck Wall Anchorage Design Tool. This tool quickly and thoroughly checks for both combined axial tension or compression with combined bending and web shear, and it also checks connections for shear and tension, including combined shear and tension interaction at the supports. Web crippling is also checked at supports for inward loading, all in service of using the metal roof deck to brace a concrete or masonry wall against out-of-plane forces. Let's jump in. First thing you'll notice, looking across the top of the tool, are a lot of different tabs. We'll spend most of our time here in this summary tab. That's going to have a lot of our main inputs and then our outputs. But some of these can be useful for digging into some of the deeper calculations, or in the case of the prying action tab, actually doing a quick side calculation in order to calculate one of the numbers we need here. I do want to point out that this tool does not check surface load deflection of the steel deck or load combinations that do not consider axial loads, but might govern if there are large gravity or vertical inward or outward wind loads. This top portion here is going to describe the demand that's put on this building, the diaphragm, the wall, the connections. All of the vertical and lateral forces are inputted up top here. And then this bottom portion is describing the products, the spacing, the connections, the geometry, all of that goes in here. And then that gets combined into this series of checks shown here as summary of calculations. So 1-span, 2-span, and 3-span deck conditions, the different axial and bending combination, connection strength, web crippling at the wall and in the field. So with all of that, we're presented with this series of ratios that all need to be at or below 1.0 in order to safely pass. And this is all built on ASCE guidance AISI S100, as you can see listed here. And then this bottom portion is just a summary of all those inputs and outputs. So the print button up top here would actually print this as a one-page PDF. And that can be included in your job calculations. That print button right up here. These fields optional, but they will print as well if you fill them in. So project name, description, job number, your name as an engineer, etc. Moving on to this prying action tab. This is one specific calculation. So after you calculate your expected diaphragm deflection due to seismic and wind, you can punch that value in here, and then based on your roof height and the eccentricity of your connection between the deck and the ledger, that'll calculate your X value. So that's your prying action displacement, and then that can be inputted back here in the summary tab, specifically in these two fields for seismic and wind. Moving on to the axial and bending tab. This tab is going to show all of the different calcs that are used for the equations to figure the axial and bending action. So all of that is listed here. You can see page 1 of 11, so there's quite a bit to go through. Very thorough, trying to be very transparent. And all of that can be displayed here and printed as well if you need that for your own reference. The connection wall and connection field tabs, again, just showing some of those background calculations. In this case, at the wall, where that deck is sitting on the ledger, and then in the field, that's going to be more for the deck attachment patterns and how it's fastening to the joists and the side laps. You can see our assumed values here for the connections made by other manufacturers, and then just how all of that comes together. And again, those calculations, multiple pages worth of them, you're able to go through at your leisure. So just showing that connection field tab here, structured very similarly, but as I said, analyzing that field condition. The V and M derivations tab is for reference, and that documents the equations that are used for the shear and moment calculations when axial forces are present specifically. So you can see kind of how that gets interpreted and just kind of showing our work for where we came up with some of these. And then that attachments pattern tab, similar to V and M derivations, just for reference, nothing to interact with, but it just shows for the given deck types, the profiles, the widths, kind of where those different connections would fall within that arrangement, just some of that geometry. So we'll go back to the summary tab here, and I'll point out that I'm about to get into an example here that I pulled from the Roof Structure Design Guide, written by my colleague Pat Bodwell. That's available as a free PDF download at vercodeck.com. And if you're following along, this is going to pull from chapters 6 and 8 from that book. In reality, all of these numbers would come from previous calculations that you've done on your project so far. So you know how high the wall is, you know what kind of diaphragm deflection is expected, you know what kind of loading the building code requires, and what you're calculating for wind and seismic. So that's where these numbers would come from. And then based on that, you would select some products that you think can handle it. And then that's when you would check and you could kind of iterate it from there. So for this example, we're looking at a single story, 151,000 square foot warehouse out on the west coast of the United States. And then with that, we've got some loading to assume here. Superimposed dead load for inward loading, 5 PSF. And for wind uplift combo, that'll be 2 PSF. There is no live load, but there is roof live load. That'll be 20. Wind uplift on steel deck is 25.3. And same for the connections. And then wall inward anchorage load in the example, that was 423 PLF. Outward is 342. And that notional load for wall anchorage structural integrity was 124. The seismic wall anchorage load there, quite a bit higher, 1,985, because this is out on the west coast. And I'll point out the note there on just how that F sub P is calculated. The 1.4 increase, we will take care of that within the tool. And that's kind of noted here as well, just to try to put some visibility on that. So this needs to be at a 1.0 E value. SDS ended up being 1.0. Seismic design category is fine. Wall construction is fine. This is figuring a concrete wall. And then for the deck, this first category is roof deck. That's the default because that's probably what you're looking at, but we do support acoustic roof deck, non-composite and composite decks without a concrete fill. So just the bare decks can be analyzed also. But in this case, we will be looking at the 1.5 punch lock B deck. So 1.5 PLB. 20 gauge grade 50 is fine. Joists were spaced at 8 foot, so deck span is fine there. For the steel deck bearing, we're going to adjust that slightly. It's 2 inches on the wall rather than 3. For the deck attachment, this example was using Hilti pins, specifically the HSN 24. So we'll get those in there. Grade 50 is fine. Support thickness is fine at 1/4 inch. And then 36.7 also fine. For the prying action, our previous calculations showed that that was going to be 0.01. And then again, that was at the wall. In the field of the diaphragm, some of the same information. So HSN 24, grade 50. Support thickness, we're actually going to drop that down to the minimum. So 1/8 inch, just to be a touch conservative, because we don't know how all the joist designs are going to go. Lapped end conditions, that we can do both ends butted or one end butted, one end lapped. For the end connection, it was a 36.7, and then in the field interior connection, it's 36.4, which is commonly done in some parts of the country, kind of mixing and matching connections to try to minimize them where they're not needed. And then based on all those inputs, I can look at my summary of calculations here, and just scanning through the different ones here, it looks like everything passes. There are a few that are pretty close to capacity, so 0.95, 0.99, 1.0 in fact. So if there are any changes to this design, or some of the products change out, someone wants to use a lighter deck, some of the loading increases due to different analysis, some of these may slip into failure. And that's where the power of this tool comes from, is having that visibility, knowing what's failing, so that you can jump right into adjusting that particular attribute of the design. And that's the bare deck wall anchorage tool. It's an exceptionally powerful tool, taking a series of material property lookups and complex equations and transforming it into one simple check. And with that, happy specifying.